So how can we calculate gravitational potential and kinetic energy? Starting off with gravitational potential energy, EG, we're going to calculate that with the formula mg delta h. And this is an equation we covered in class about where this equation comes from. So we know that m is clearly just the mass, as always. G is the gravitational field strength, which on Earth, 9.81 newtons per kilogram. And then h, which is, or delta h, which is our change in height. Okay? And then, okay, so basically one thing that's important about gravitational potential energy is if we're raising something up or lowering something down, we always need to have a reference point, so a starting point. We'll get more to that when we go to the calculations. Kinetic energy is just another equation, EK for kinetic, energy kinetic. The equation for that is 1/2 mv squared. This one's pretty straightforward. It only considers the mass of the object and the speed of the object. Notice how this is not a vector, right? This is not velocity in this case. We just want to know the total speed of the object to calculate the kinetic energy. Kinetic energy doesn't depend on what direction the object is traveling. It's just basically what speed is it going. We're going to skip this summarized question. What does the potential mean in gravitational potential energy? We'll talk about that one in class. So first of all, problem one. You lift an apple 1.2 meters upwards. The apple has a mass of 100 grams. How much energy did the apple gain? I would recommend all these questions on this page. Try them yourself before watching the solution. It's just plugging stuff into the equation and keeping track of the units, but you should be able to tackle them all. So try them all first before you watch the solution. So in this case, for question one, the apple is being lifted up. And when it's being lifted, the height's being changed. We know we're going to have a gravitational potential energy that's added to that object. So basically, EG equals mg delta h. We're given the mass of the apple. I should have done this on the left. But that's okay. I'll just do it here for today. We're given the mass is 100 grams. And we are given that the height, or the change in height, how far you've lifted it, is 1.2 meters. And we also know that G is 9.81. I'm not going to write that down as a given. That's just a given because we're on Earth. Now, one thing you should realize about this, is there anything we should keep in mind? Well, if you look at the units for gravitational field strength, 9.81, is newtons per kilogram. And because of that, we should actually convert this to kilograms. 100 grams is 0.1 kilograms. Now that we have everything, we can just plug it into the equation. Mg delta h, so 0.1 kilograms times 9.81 newtons per kilogram times 1.2 meters. Okay? When you do this calculation, it just comes out to 1.2 joules. Rounded to two significant digits, 1.2 joules. There we go. Next question. Try it yourself. We have 3 different points where you have to calculate the gravitational potential energy of the person on the sled with a mass of 45 kilograms. I'm just going to label this here, actually. M equals 45 kilograms. And actually, before you pause it and try it yourself, we have to establish, when there's a question like this, that it's like a height above something or below something, we have to establish our reference point. And in this case, the reference point is the ground, or the reference level. So we're going to consider that height 0, and we're considering our height above or below the ground with respect to that. So any height, anywhere we're going up from there is going to be positive, anywhere we're going down from there is going to be negative. So essentially, the height for point A is just going to be 15, the height for point C is going to be 5 meters, and height for point B, well, you're at ground level. So if you're at ground level already, you basically have no gravitational energy, right? You're just at ground level. You can't do any work at that height. So again, you can pause it and try it yourself. In fact, pause it here because the answers are going to pop up because this is a pretty straightforward calculation. So pause it here, try it yourself, and then unpause it. So there we go. The calculations are right there. So the only thing that's changing essentially is the height. The mass and the gravitational field strength don't change. So the answer to at point A, they have the most gravitational energy because they're the highest up. At point B, no gravitational energy because they're at the ground. And C, they have 22 or 2,200 joules of energy, so somewhere in between. So in this next question, we're lifting weights from 0.3 meters to 1.5 meters. And we can assume that's probably 0.3 meters above the ground to 1.5 meters above the ground. So if we call this the ground down here, so I'm just going to make that a 0, height of 0. We're lifting them from a height of 0.3 meters up to 1.5 meters. So the first part, A, says how much potential energy did the weights gain? So how much potential energy did you give the weights when you lifted them? And again, we're going to use our formula, Eg equals mg delta h. We know the mass is 80 kilograms. We know the gravitational field strength is 9.81 newtons per kilogram. And what is the change in height? Well, remember, change in height is the same thing. Change in anything is always the final minus the initial. So delta H is like our final height, HF, minus our initial height, HI, right? You can also just look at the little drawing that I drew, and you can see that the change in height from from 0.3 to 1.5 is going to be, what's going to be 1.2, right? Because it goes up by 1.2. So this is plus 1.2 meters is the delta H. So that will be that, 1.2 meters. When we calculate this, 80 times 9.81, I know the answer's there, I just want to double check, times 1.2, yeah, about 940 joules. Now, so that's the answer, that's how many joules we needed to do that work. How much, if we lower the weights, does the calculation change at all? So if we lower the weight from the 1.5 to the 0.3 meters. So let's think about it. The mass doesn't change. We know that, right? 80 kilograms. The gravitational field strength doesn't change. 9.81 newtons per kilogram. What's going to be the delta H, though? Remember, if we think about delta H as the change in height as the final height minus the initial height, so delta H, the final HF minus HI, the final height is the 0.3 meters. And the initial height is 1.5 meters. So the delta H in this case is actually going to come out negative, which makes sense. You're lowering it so that the change in height is actually negative. So we should put in negative 1.2 meters. And the answer comes out the same number, but it's negative joules. So essentially what it's saying is that the weights lost 940 joules of gravitational field strength, which makes sense because it's lower. This is the last problem for gravitational energy. We know because we're raising up an object. So in this case, we're asked to find, I'm just going to write the equation, we're asked to find the mass of the object. So obviously, we're pretty good at this by now. We can rearrange that equation for mass. So the mass is just going to be equal to the gravitational potential energy divided by G delta H. Okay? We know the gravitational field, or the gravitational energy is 1,000 joules. The G, the gravitational field strength, is 9.81 newtons per kilogram. And the height, the change in height, is raising by 10 meters, so plus 10 meters, or just 10 meters. If we do that calculation, it should give us the mass. And if we round to two significant figures, it comes out to 10 kilograms. There we go, not too bad. So in this question, we got to find the kinetic energy. It's an object that's moving, in this case a snowball that's moving. The equation is 1/2 mv squared. So all we got to do is plug in what we know. Are our units okay? Kilograms and meters per second. Those are okay, right? Those are the units we're always looking for to keep the calculations really simple. So we have 200 kilograms for the mass. And then the velocity is 5 meters per second squared. There we go. And if we do that calculation, it should come out to, rounding to two significant digits, well, actually, it comes out to exactly 2,500 joules. No. Okay, and last question, 6, with 2 parts. Again, try these yourself, pause it, try them yourself, and then unpause to see what's going on if you're stuck. So an object has a kinetic energy of 2 kilojoules, and we know that that's just 2,000 joules, right? So let's just change that right off the bat. If it has a velocity of 5 meters per second, find its mass. So we know EK is 1/2 mv squared, and we want to find the mass. So we got to simplify this equation or solve it for m. Alternatively, you could just plug in the numbers and solve for m that way, but I'm going to just rearrange this equation. So first of all, if we're a little bit rusty at this, to get rid of that 1/2, I'm just going to multiply both sides by 2 to get rid of that 1/2. That 2 and that 1/2 are going to cancel out. So then I get 2ek equals mv squared, and then I can just divide by v squared. So I end up getting that m is just equal to 2ek over v squared. There we go. And now I could just plug in what I know for the mass. So mass is 2 times 2,000 joules over 5 meters per second squared. There we go. If I do that, 2 times 2,000 on my calculator divided by 5 squared, I get 160 kilograms exactly. Okay? The most common mistake with this is people forget about that squared. So just keep in mind that whenever you have kinetic energy, there is always a squared on the velocity. Okay, and lastly, if we have a mass given, how can we find the velocity of that object? So same idea, EK equals 1/2 mv squared. It's moving object, so it has kinetic energy. We got to solve for v. So I'm going to do the same thing I did the other time. I'm going to multiply both sides by 2 and then divide by m in this case to get that v squared equals 2ek over m. If you're confused about that, try the actual calculation in your own method, but that's what you should get. And then to solve for v, we got to take the square root of both sides. So v is equal to the square root of 2ek over m. There we go. If we just plug in what we know, 2 times ek, which is 2,000 joules, right, from up here at the top, from the question 6. And then we're going to divide that by the mass. And the mass in this case is 10 grams. Oh, off to the side, let's convert that. 10 grams, well, we got to divide by 1,000 to get it into kilograms. It's 0.01 kilograms. So there we go, 0.01 kilograms. And that should give us our final answer. Let's just double check. 2 times 2,000 divided by 0.01. And then we have to take the square root of that to get, 632.4, or rounding to 2 significant figures, 630 meters per second, because it is a speed. There we go.